Okay. Does everybody see the desktop? Is anyone there? Let's see.
Yeah, we can see the desktop.
Okay, great. Uh-huh. Okay, let me set things up. Okay. Um, so today we're going to continue talking about virtual memory. We're going to start talking about the modern way of doing virtual memory, the paging. But first, let me point out there's a little extra comment here on the website. One of the students in the computer science department is working on a research project, and she'd like to ask people to fill out a questionnaire that she has. So the questionnaire kind of looks like this. You can just click on the link and you could answer some questions of hers about teaching. Okay, her name is Isis. Uh, yeah, I'm sure you can. If you want to ask her a question, you can get a hold of her, or if you have a question about, it, you could ask me. But yeah, if go ahead and if you have time, fill out that form and help her with her research. Okay, and let's see. Okay, so let me get the I added some notes. We're working with this zip file on Windows Virtual Memory, but I added some notes this morning and I haven't had time to upload them to the server. So I'm gonna get the notes off of my hard drive. Okay, so we're gonna work with, okay, so want to start talking about page virtual memory. Hey, let me let these things copy. Oh, my computer's acting slow. Okay, okay. Remember, this is our starting point, that we want to translate from virtual addresses to physical addresses. And we've got this box here that represents the memory management unit. Okay, and so far, that box is empty here because we want to talk about lots of different mechanisms for translating virtual addresses into physical addresses. The most basic mechanism was just a single pair of base and bounds registers. Okay, this is real simple, real easy to understand. It was real easy to implement in the old days, and it's a good starting point because it helps you build the idea of what we mean by a virtual address space over here. The CPU sees a virtual address space, and the memory management unit translates those virtual addresses into physical addresses here in a real straightforward way, just uh, by adding the virtual address to the contents of the base register. Okay, and then we extended that to a, several pairs of base and bounds registers. If you allowed yourself to have several pairs of base and bound registers, then you could do a lot more things. Um, let's see what happened to the. Oops. Oh, I forgot to put the picture we drew yesterday in this folder. Okay, we drew the picture for multiple pairs of base and bounds. They're in the notes from Monday, but I'll copy them into this folder too. So when you have multiple pairs of base and bounds, the goal of it was we were able to do a bunch of things. Like we could have uh, processes share we solved there was three major advantages to having multiple base and bounds. One was we could help solve the problem of internal fragmentation. We could let two processes share some virtual memory, physical memory. So, for example, they could share libraries. Like that's the example we looked at. They could share libraries of code. And then the other thing if you worked with, if the operating system would combine physical memory with a hard drive, you could have virtual memory for a process even appear to be bigger than physical memory. because you could have multiple segments, but some of them could be copied to the hard drive. Okay, so you got, by having multiple pairs of base and bounds, you could get several advantages over just a single pair of base and bounds. But the big disadvantage was the external fragmentation, the idea that there's these gaps between the processes. So like here, there's a process, there's a segment here and a segment here, and there's no segment here and there's no segment here, but memory is fragmented. Okay, if you wanted to load a really large segment that didn't fit in this gap, you'd have to move this segment up to combine this empty space here with this empty space here. Moving segments is really time consuming. So this external fragmentation problem is a huge problem. Right? So multiple base and bounds solve several problems, but they still leave a big problem: external fragmentation. And paging is the way to completely solve the external fragmentation problem. With paging, we'll see that there actually is no external fragmentation. So it works out really nicely. There is no external fragmentation at all. Okay, so paging takes a while to explain. It's kind of a slightly, well, it's a modification of multiple base and bounds registers, but not in a really obvious way. Okay, so let me draw a picture. Okay, see if I can draw a good picture. Here's our starting point. Over here, I'm going to draw just a part of that. I'm going to kind of redraw the picture in a little way. Over here, I'm going to think of virtual memory. And over here, I'm going to have physical memory. Okay. Now, virtual memory is an array. So I'm going to draw a picture of an array. Virtual memory is an array, and physical memory is an array, possibly of a different size. Okay. Now, we've been thinking of these as array of bytes. Okay. But right now, we're going to switch slightly to a different idea. Remember, we just were dividing physical memory into segments. And when physical memory was divided into segments, the segments could be different sizes and there could be gaps between them. And the trick is to not think in terms of segments. What we're going to do is we're going to divide virtual memory and physical memory into something called pages. So here's, if I can draw that well, okay. I'm going to divide virtual memory into sections. You might call them segments, but they're called pages. These pages are, in most modern computers, they're 4,000 bytes. So virtual memory is an array of pages. Okay. So here, virtual memory is an array of pages. Each page is 4 kilobytes. Okay. Then we're going to do the same thing over here. Physical memory is also going to be an array of pages. Okay. Over here, physical memory is an array of, but we're going to give them a different name over here. We're going to call them page frames. Over here in virtual memory, we're going to say that this is an array of pages. Over in physical memory, we're going to say it's an array of page frames, the same size as pages, 4 kilobytes. Okay, so over here, I would draw page frames the same size as pages. There's a page frame, there's another, but there could be more of them over here. Since physical memory is bigger than virtual memory, I'll end up with more page frames over here. Okay, so I have 2 more page frames on the page frame size. Okay, so we're going to think of virtual memory as a collection. So this is one process's virtual memory. Pardon me? Did somebody say something? Okay. Okay. So each process has its virtual memory cut up into pages, and the physical memory that all the processes share is cut up into page frames. Okay. Now, what we're gonna do then is we're gonna allocate his pages to page frames over here. So let me let's me do it this way. This is gonna be page 0. This is page 1. This is page 2, page 3, page 4, and page 5. Okay. And then over here, these are page frames. There's page frame 0. There's page frame 1. There's page frame 2. Now, these are not addresses. These numbers over here are called page numbers, and these numbers over here are called page frame numbers. Addresses address bytes inside of the pages. Okay. 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 Now, in between here, I'm going to have a page table. Okay. So now I'm going to have something called a page table. This is actually what's inside the memory management unit. Okay. So I could put a little box here. I'm going to say, oh, I'm sorry. Here's the memory management unit now. The memory management unit is now called the page table. Okay. The page table is going to be an array of the same size as this guy. So this is a 1, 2, 3, 4, 5, 6 element array. So I should have a 6 element array over in the page table too. So I see if I can fit 6 elements over here. I should have planned ahead. So there's okay. All right. So the memory management unit is a table with as many elements in it. Actually, it's an array with as many elements as there are virtual pages over here. Okay. Now, here's the idea. This piece of virtual memory has to be somewhere in physical memory. Okay. And what I'm going to do is I'm going to say maybe it's over. Whoops, that wasn't what I wanted to do. Maybe it's over here. So I'm going to write a 0 here. The number I write in here means that this page frame, this page is really over here in physical memory. Okay. So then what I'm going to do is up here, I'm going to, in the page table, I can barely get, I'm starting to run out of room. I didn't plan ahead, right? Okay. This thing says the page table tells the CPU that when the CPU wants to access this page, it should find page 4. Well, see, this is entry 0. Okay, so page 0, you look at entry 0 in the page table, and the page table says that this guy is over here in page 0, in page 4. Okay, now maybe page 1 is up here. Well, let's see. Let's put page 1 over here. His page 1 is over here in physical page 2, in page frame 2. So in the next entry of the memory management unit, we would have what did I say it was? 2. Okay. So page 1 of virtual memory, you look it up, page 1 is in 2. It's in page 2 of physical memory. Notice that this is going to be weird. These two contiguous pieces of virtual memory are not contiguous and not in the right order in physical memory. And we're going to have to see how this kind of works. Right now, I'm just showing you how to think about how a virtual address space is going to be laid out in physical memory, but using a page table. Okay. Now I'm supposed to go through here, and I'll do one more. Let's suppose this guy's page 2. Maybe it gets put down here. Okay. So his page 2 is going to be in page frame 5. Okay. Now let's suppose that this process doesn't need a lot of virtual memory. So let's suppose that this process doesn't need pages 3, 4, and 5. Okay. So let's suppose that these pages are empty. So I don't know, should we see? Suppose that this is like not used.
All right, stop watching those coin videos I got.
Okay, so let's say, let's see, empty. And suppose this one also is just not in use. So we'll denote it as empty. Okay, and we'll denote this one as empty too. Okay. All right, so now you still have to have something over here in the memory management unit. Okay, so let's see. So there has to be something down here for entry 3, entry 4, and entry 5. Okay. Now this is computer memory. There has to be a piece of data in here. So there might be a number in here. Like, since maybe the number is like, let me put. Suppose there's the number 42 in here. I didn't draw it in the right place. We need something to say that this page in memory, this virtual page, you look it up and get the number 4, that tells you that it's down here. But for example, for this one, when we look it up, we really want something to tell us that whatever number's inside here isn't valid. So what we're going to do is we're going to add to this page table another little chunk. We're going to give this page table a little extra piece. This is like a 1-bit array. Okay. So I'm going to add a little 1-bit array to the page table. This 1-bit array is called the valid bit. Okay. So it's called the valid bit. So I'll write it up here. Okay. Now what the valid bit tells us is that this page table entry here is valid. So it holds a 1. And the next page table entry is valid. So it holds a 1. There's a 1 here. The next page table entry is valid. There's a 1 here. Now we want to say that these 3 page table entries are not, even though there's numbers there, in a computer, you can't have a blank piece of memory. There's always some bits there. Okay, so we want to say here that those bits don't have any meaning. So we put a 0 in these bits for the saying that these are not valid entries.
You should disable the screensaver.
Pardon me? Okay.
Sorry, I'm talking to someone else.
Oh, okay. All right. Now, see. Okay. So now the idea is that here's some process with virtual memory. He's using up this much virtual memory. This is really what he's using. And he's got this part of virtual memory here he's never going to touch. He doesn't have any data in these pages. So his page table will say his page 0 is in page frame 4. So his page 0 is over here in page frame 4. And his page 1, he looks in the page table, the CPU looks in the page table and sees, oh, the page numbered 1 is actually in the frame numbered 2. Okay, so the page numbered 1 is in the frame number 2. A lot of times we use the abbreviation pages on the left side, frames on the right side. The book calls these virtual pages, and it calls these page frames. Okay, so see, I've got, this is an array of page frames. This is an array of pages, or what the book will call them is virtual pages. There's a lot of slightly varying terminology from book to book, but the word page frame is almost always used to be this side. Page frames are pages in physical memory. Okay, so when the CPU is running this process, it knows that pages 0, 1, and 2 of the process are in pages 4, 2, and 5. And then it doesn't really care what numbers are in these boxes. So for example, there might be a number here like 72. And there might be another number down here like maybe the number 0. Okay. But these numbers really don't mean anything because these bits say that these are invalid numbers over here. So, okay, so the CPU knows that these page table entries don't have any meaning. Okay, okay. Now, here's the key idea. There is no such thing as external fragmentation. If you look over here, you say, well, memory's fragmented. I'm using this page frame, and this page frame, and I'm not using these 2 page frames here, this page frame here, these 2 page frames here. Suppose a process comes along and needs 5 page frames. Okay, this is the key idea. Suppose a process comes along and wants 5 page frames. Well, there's 5 available, 1, 2, 3, 4, 5. Do we need to move anybody around in memory? The answer is no, because I'm going to construct another page table now. And I'll show you that the other process, so I'm going to construct a page table for another process. Now you can't have well, you can, if you have 2 CPUs, you can have 2 page tables active at a time. So let's imagine that there's actually 2 CPUs. Okay, I'm going to draw I don't have room to draw the virtual memory for the other process. I'll just draw the page table for the other process, but not his virtual memory space. Okay, so the page table's in 2 pieces. There's the page table and the valid bit. Okay, let me sit down and draw my little lines. I need a 1. How many of these I need? 1, 2, 3, 4, 5 of them. Kind of squish this in there. Okay, now I have a process that wants 5 pages. So I'll need to give them entries for 1, 2, 3, 4, 5 pages. Okay, so here's what I'm going to do. I'll put this second process's, the second process has, okay, here's 0, 1, 2, it's kind of sloppy here. Okay, I'm going to use, I'll use a different color for the other process. Okay, now here's suppose I take the other process and I put his page 0 over here. And I put his page 1 here. And I'll put his page 2 here. And I'll put his page 4 here. And I'll put his page 5 up here. Okay. So his page tables say, let's see, his page 0 went into page frame 1. His page 1 went into frame 3. Now notice that I didn't have to compactify. I didn't have to defragment memory. When memory appeared to be fragmented, because I was using page frames 2, 4, and 5, and I had 6, 7, 3, 0, and 1 empty, when somebody else comes along and needs 5 page frames, their page frames don't have to be contiguous. So I could squeeze his pages anywhere I want. Okay, so actually, let's see. So 0, 1. His page 2 went where? In 5. His page 3 went, oh, I forgot a page. Let's see, what did I goof up something? Oh, I forgot 3. See, I counted wrong. I went 0, 1, 2. I skipped 3, went 4, 5. This should have been 3, 4. Let's see, can I edit these? Let's see. Does the eraser tool erase numbers? Let's find out. Yeah, okay. So I can, that was, okay, these two are wrong. Okay, so this was supposed to have been 3, and this is supposed to have been 4. Okay, so his page frame 3 went into, his page 3 went into frame 7, and his page 4 went into 0. Okay, actually over here I can draw his virtual memory. So let me over here draw the virtual memory space for this other process. So this is virtual memory. This would be virtual memory 1. Okay, and over here I'll do virtual memory 2. Okay, so let's see. A virtual memory space would look like this. Okay, this is going to be virtual memory 2. Okay, so I've got I have in physical memory, I've got 2 virtual memories systems mapped into physical memory. This is page table. This is page table 1. Okay, and over here is page table 2. It's a lot easier to do this on a chalkboard, faster too. Okay, now over here, let me just see if I can quickly map out his virtual memory. Okay, so he's got, these are the pages of virtual memory. Okay, and page 0, page 1, page 2, page 3, page 4, and page 5. And let's see, now, where were they placed in physical memory? Okay, page 0 was over here in frame 1. Page 1 was over here, be mapped into, well, okay. It will, actually, I didn't do that over here, so that's not really what we want to do. So we don't need, if we want to know where page 0 is, that's what we do. We look in the page table. Page 0, we look in its page table. We say, oh, page 0 is over here in frame 1. So that's page 0 of virtual memory process 2. Okay. The key idea, I mean, it's kind of a elaborate bunch of steps, but the key idea was that there was no fragmentation of physical memory. When it looked like memory was in pieces with a page used here, a page used here, and a page used here, empty here, empty here, empty here, here, and here, It looked fragmented, but it never really is fragmented. There's absolutely no external fragmentation in the page memory system. For example, if if process 1 dies, he'll free up that page frame, that page frame, and that page frame, because he's using up 3 page frames. So if he dies, oh, let's see, in our case over here, this one was empty. So I would, yeah, if I keep the pictures the same. See, this one was the one that's empty. Oh, and I didn't fill in his okay, so over here, it's one last thing to do. Let's fill in his valid bits. Okay, so this is valid, 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 and then the very last one is invalid. Okay, you can kind of barely see it. So he's got 5 valid page table entries and 1 invalid page table entry. That's because he's not using, he's using 5 page frames and he's leaving 1 empty, unused. Okay, right? Now, if process 1 goes away, he frees up 2, 4, and 5. Okay, if somebody else comes along and needs 3 page frames, they can just take up 2, 4, and 5. Now, if somebody comes along and needs more page frames than there are physical memory, we just have run out of physical memory. That there's nobody can solve the problem of having run out of physical memory. Usually, we'll see in a while that there's going to be huge numbers of these page frames. We haven't talked about how many of these there are, but there are going to be, well, you can actually figure it out real quick. They're 4,000 kilobytes. And if you have 8 gigabytes of physical memory, and see, 4 kilobytes is 12 bits. Okay, 4 kilobytes is 12 bits of addresses. In a 64-bit computer, the number of page frames is the number of bits less than number of the bits from the pages. So if you have a 64-bit computer and you need 12 bits to do inside of a page, that leaves 52 bits for page numbers. So there's 2 to the 52 page numbers, which is a monstrously big number of page numbers. Okay, so there's a lot of these, and actually there's a lot of these too. Your virtual address space will have a lot of page. Your virtual the 4 kilobytes is a pretty small size, so there's memory's going to be chopped up into lots of little pieces. Essentially, what it amounts to, memory's chopped up into lots of little pieces. Okay, let me save this before I, let's see. Don't want to lose. Okay, now this is the idea behind, there's still a lot of detail we haven't talked about. This is the rough idea of what we mean by page virtual memory. Okay, a process, virtual, key idea, virtual memory is chopped up into equal size pieces called pages. Physical memory is chopped up into the same size pieces, but they're called page frames or just frames. Okay, and then you map the memory management unit maps pages to page frames. So it's just an array. The page numbers are indexes into this array. The page frame numbers are the entries in the array. Okay, so the memory management unit is now a page table. It's an array of these entries. It's an array of these entries. Each entry is a page frame number and a valid bit. We'll actually end up putting more bits over here. When we're done, there'll actually be a whole bunch of bits over here. The page table will actually end up being not only just the valid bit, but there'll end up being quite a few bits over here. So there'll be a whole bunch of bits. Whoops. there'll be a whole lot of bits over here. And one of the things we, part of the detail we have to put in is to give names to all these bits and see what they all do. But there'll be a whole bunch of, the page table will be this one thing called the page frame number, and then it'll be a whole bunch of bits. Right now we've talked about one bit, the most important one of them, the valid bit, which tells you if this data is valid or not. And you need that bit because you can't have one of the, just in a computer, it's important to remember, you can never have an empty memory location. This thing, the page table is a piece of computer hardware. It's essentially, it's a bunch of registers in the CPU, okay? And it's in the memory management unit, and they can never really be empty. So if you look up this index 5 and you see a number here, how do you know if that number means anything? Well, you look over here, and if you see a 0, that number doesn't mean anything. If you see a 1, then that number is what you're looking for. That's the page table entry that you're supposed to go. That's the page frame that you're supposed to go over to. Okay. See, like here, 0 could mean I go over to here, but we know that 0 is holding somebody else's page frame. See, 0 is actually holding somebody else's page, but in this page table, this 0 doesn't mean anything because that bit is 0. That bit here says that that's not a valid piece of data. Okay. So similarly over here, I could put a number in here. Like maybe I put the number 2 in here. Okay. Well, 2 is somebody else's page frame. So it can't be this guy's page frame, but this bit here, it says that that's not valid data. So the 0 bit says what you're not supposed to pay attention to that number that's over there. Okay. Okay. Now let's look at some more detail of this picture here. Here's some notes I wrote that are just another way of sketching out what we just did here. Okay. Okay. We actually want to combine. I'm running out of room, but we really want to combine 3 pictures. This picture here, and some, we actually want to combine these 2 pictures. Okay. Okay. If you try to combine these 2 pictures, this is what goes inside here. Okay. This thing here is what would be inside here, and virtual addresses come in here. So now what we have to do is explain how the virtual address and the physical addresses are related to what's over here. We were kind of sketchy over here. We really notice over here we didn't talk about addresses over here. We talked about pages and page frames. Okay. Inside these pages are the bytes, and inside these page frames are the bytes. The bytes have addresses. So when we go over to this picture, this is over here, this was an array of bytes. Okay. We now want to kind of merge these 2 pictures together and start talking about the address of individual bytes over here and how those addresses get translated to individual bytes over here. What we did over here is we showed how to translate a whole page over here to let's see, that page translated to that page frame. This page translated to that page frame. Okay. But what about an address in this page? Okay, this page is 4,000 bytes. So if I want the address, one of the bytes in here becomes a byte in here. So I want to know the address of the byte in here. I want to talk about virtual addresses mapping to physical addresses. Okay, so that's what I mean by combining these 2 pictures is, add the CPU and add the idea that a memory is now an array of bytes. Okay, now here's what we're going to do. It's kind of sketched out here a little bit. Okay. a virtual address, okay, is going to be chopped up into two fields. Okay, so a virtual address over here, see, we say it's n bits. The virtual address is n bits. The virtual address is going to be chopped into two fields. Some of the bits, the lower order bits, are called the offset, and the higher order bits are called the page number. Now, this is where it kind of gets back to what we were doing with base and bounds registers. Virtual addresses in base and when you had segments, multiple base and bounds registers, virtual addresses were cut into two pieces. One piece identified the segment, and then one piece was the offset into the segment. And essentially, that's what this is like having lots of segments, because we're taking an address and chopping it into two pieces. What in the case of the base and bounds, this number chose which base and bound register to use, and then this was the offset into the segment. Now, this, in our case here, now this number chooses which entry in the page table to look in. Okay, this page number is an entry in the page table. And then this offset is how far into a page you are. Okay, here's a page. It's actually, okay, if I wanted to, I could see if I can. Up here is a 0 also. That would be byte 0. Okay. There's a byte 0. And right below it is a byte 1. And right below it is a byte 2. Okay. Notice that these, over here, I'm thinking of the byte addresses, 0, 1, 2. Over here, these are the page addresses. This is page 0, page 1. This is byte 0, byte 1, byte 2. These numbers here, now, what about this number down here? This is the first byte of the second page. Okay, it would actually be byte 4001. It would be byte 4000. Let's see, it's actually 4000. Does anybody remember what's 2 to the 10? Was it see, 1024, 2004, 4096. Okay, that's the first byte in the second page. There's each page is 4 kilobytes. So the first byte in the second page, let me move that up a little bit. The very first byte in the second page be 4096. Okay, but oops. Okay, but it's the 0th byte in that frame. So this is this byte here, the first byte in this page frame, has address 4096, but he is the offset of 0 in that page. Okay, so that byte there would have an offset of 0 in the page number 1. But page number 1 would be this bit here, which would actually be the number 4096 when you look at powers of 2. Okay, so if you put a 1 there and you put a 0 there, and then of course you actually have, see, there's the 0 offset in page 1, but that's in bit 13. This is bit 13 over here, because we've got to go past 4,000 bytes. So this is page 1. Okay, so I would actually have all zeros here. See? So the address of this byte would be 0000001, but that 1 is really saying it's in the first page, it's in page frame 1. And then the rest of its address would be all zeros. That's saying that's its offset. It's the first byte in that page frame. Okay. This is the index into the page table. Okay. So then that virtual address, you look it up in the page table and you get out, and the page table tells you 2. So then over here, we would go, we would translate that guy by going, okay, but it would be, notice I wrote 1 0 because that's the number 2 in binary. So page 1, I look at it in the memory management unit, translates to page frame 2. So I do that in binary and I get 1 0. So that's in page 2. And then the offset is still 0. Okay. So this first byte in the second page, so there's the first byte in the second page. That's its virtual address. That's the address of byte 4096. Okay. I take its page number, use it as the index into the page table. So that's page table entry 1. And I look in the page table and I see 2. So that means I translate the page number to the page frame number, and I'm starting to build a physical address. Okay, then that is the second page frame, but I'm using the same offset. Okay, now here's the code. Here's what that looks like if you write it as a piece of code. A physical address is made up by taking a virtual address, getting the page number field, that's this field, the page number field. Look up the page number field of a virtual address. Use that as the index into an array. See, I used array notation there. Use that as the index into an array called the page table. In the page table, look up the page frame number field. That's this field in the page. The page table has this field and it has the valid field, and it'll have a bunch of other fields also. Okay, so take the virtual address, take the page number field, which is the higher order bits of it, take the page number field, use the page number field as an index into the page table, and then look up the page frame number in the page table. Okay, that is the first part of the physical address. Then you concatenate onto it the offset part of the virtual address. See, that's this part here got copied down to here. Okay. This part's an index into the table. You look up that number as an index in the table. This is the entry in the table. You copy that down here. That's the left half of the physical address. And then the offset here, however much you're offset into this thing should be how much you're offset into this thing here. You know, your offset into the page should be the same as your offset into the frame. So you always copy the offset from the virtual address to the physical address. Okay. Now, what if somebody goofed and they tried to access one of these pages down here? So suppose the program is running and the program accidentally tries to access one of these pages down here. When the CPU sees that it's supposed to take the page number and look in the page table at that page number, it checks to see if the valid bit is a 0 or 1. Okay, so before you do the address translation, you need to do an if statement. You have to say, well, take the virtual address, take its page number as an index into the page table, and in the page table, look up the valid bit, look up the valid field. And 1 means true and 0 means false, just like in C. So if the valid bit's a 1, go ahead and do the address translation. If the valid bit's a 0, that means you've accessed something that's really empty memory. See, the valid bits being 0 means that this is really supposed to be not used. Okay, so this guy's virtual memory space, he's got 3 page frames allocated to him, and these pages are just not to be used. He only doesn't, when this program was compiled, the compiler determined that this program only needed a little bit of its virtual memory space. So the compiler put all of the data and code in this path of virtual memory space and said, well, this isn't needed. So there's no point wasting page frames on unneeded memory space. So these entries are considered empty. They get 0 valid bits. And if you do goof up in your code and issue one of these addresses down here, you will get a interrupt. You'll get this. That's now where this interrupt goes back here. In this picture, the thing that says something went wrong in memory management unit, interrupt the CPU to say that there's an invalid address. Now it's because of the valid bit. Okay, it's this thing right here. You looked in the page table, you looked at a entry in the page table, and then looked up its valid bit, and if it's 0, you issue a memory error. Okay. Okay. Now, this is notice I've got a picture here, and a bunch of text over here explaining it. There's a lot of moving pieces to virtual memory. It takes a little while for people to get used to it. Okay, it does take a while to get used to this concept of virtual memory, and right now we're keeping it real simple. Like, we're only going to put 1 bit over here in the page table. Later on, we'll see several other bits in the page table, and then we're going to add the hard drive to the picture. Remember, we said that with segments, it was possible to have, if threw the hard drive into the picture, it was possible to have a process as this virtual memory actually be larger than physical memory. The same is going to be true here. We can add the hard drive to the picture, and we could have a process's virtual memory actually be bigger than physical memory. There's going to be all kinds. We're going to let processes share virtual memory, or I'm sorry, physical. We're going to let processes share physical memory. Okay. So we're going to keep adding to this, but we'll just keep doing examples over and over again, because it just takes a little while to get used to this system. There's just a lot of little moving parts to it. Okay. Over here, I gave the algorithm and the data structures. So the idea here is that this is a very programmer's way of thinking about something. I've got a system over here, and I should be able to think of the system as code and data. Okay, so for example, here, the page table is an array of page table entries. So one row of this table is called a page table entry. Right now, I'm deciding a page table entry is a page frame number field and some other bits. Okay, like this one, we'll think of this one as the valid bit. Then there's going to be some other bits. There's going to be the present bit. And let me think, what's another one? Read-only bit. There'll be some other ones there. So there's going to be the valid bit, the present bit, the read-only bit. Oh, there'll be something called the guard bit. Okay, there'll be a whole bunch of bits that we're going to add to the page table entry, and we'll give meanings to them and see that each bit solves some clever little problem. Okay, so the page table is an array of page table entries. The page table entry has got a page frame number field and some bits. Okay, how big is the page table? Well, it's 2 to the n, where n is the number of bits. It's the number of bits in a virtual address page frame number. Okay, see, virtual addresses are divided into 2 parts. There's the offset part, okay, and what we call the page number part. Okay, the page number part are these guys over here. Okay, the offset is the addresses of the bytes inside here. Okay, the offset is, let's see, let's do a specific example. Let's suppose we have a 32-bit computer. Okay, let's suppose that we have a 32-bit computer. So virtual addresses are 32 bits. Okay. Now we said that the page table is 4,000 kilobytes. 4,000 kilobytes means that there are 12 bits in this part here. It takes 12 bits to address 4,000 kilobytes. Remember, 2 to the 10th is 1,000. So 2 to the 11th is 2,000. And 2 to the 12th is 4,000, 4 kilobytes. Okay. So that leaves this part here as 20 bits. Okay. So there's 20 bits up to here. And so between here and here are 20 bits. Okay, so there's 20 bits through here. Okay, and then there's 12 bits from here to here. Okay, so a 32-bit address falls into two pieces. The 20-bit part, which is the page number, and the 12-bit part, which is the offset. That tells you how far into the page you are. Okay. Now, if over here now, this part's still 12 bits. This part here is still 12 bits. Okay. So that means this part over here, see now, oh, on a modern computer, this is 48 bits. We've mentioned a few times before that on a modern computer, that the physical addresses coming out here have 48 bits here. Okay, so we'll treat this as a 48-bit physical address. Okay, so that means over here there's a lot more bits. Okay, so what's 48 minus 12? That's what? There's 36 bits here. Okay, so that's 36 bits in what's called the page frame number, 12 bits in the offset, 20 bits in the page number, 12 bits in the offset. Okay, so we have 32-bit addresses going in, 48-bit addresses coming out. Okay, now that means that there are 2 to the 20. This array is size 2 to the 20. Okay. Now 2 to the 20 is let's see, that's a megabyte. That means this is a million, and the page table has a million. In this case here, of a 32-bit address space. Okay, the page table has a million entries. It's not a small table. There's a million entries in the page table. Okay, because that's 2 to the 20th. Okay, so down here, the page table now is 2 to the 20. Okay, so the page table's a million entries long. So there's the thing that determines how big the page table is. Okay, there's one entry in the page table for every page. Okay, and there's as many pages as there are 2 to the n of this many bits here. Remember I said there's a lot of moving parts to this this stuff. So it's going to take a little while to get, you know, where you get real comfortable with all these words. Okay, so long list of words: pages, page frames, page tables, page table entries. Yeah, there, and offsets, page frame numbers, page numbers. So, you know, there's a lot of words, and it helps to write them down and to try to familiarize yourself, get used to these words. I mean, a good way to learn this is make up a list of the words and then try to write down their definitions. You know, just, you know, list out all the terms and then try yourself to at least sketch out the definition of each one. Page table entry, page frame number, page. Okay, page versus page frame, page table entry versus offset. Okay, so it's a lot of moving, but notice that it's a lot more complicated than base and bounds or even segments. But the complication comes from we solve a huge problem, no external fragmentation. Okay, so we solve a really big problem, and it's well worth the effort on a modern computer to have this level of complexity, because it absolutely solves it's not common in operating systems and computer science where you can absolutely solve a problem. Usually you have a compromise. In this case, the external fragmentation problem is just gone. It's actually kind of a clever design, because a fairly big problem, external fragmentation, is just gone. Okay, and so that's actually a great thing, but it comes at the cost of a fairly complicated system. Uh, paging is considered a not a trivial thing to understand, and it just keeps getting more and more complicated. For example, we're going to use 32 bits most of the time for our ideas. Okay, if I switch this to 64 bits, something blows up. Okay, this is now 56 bits here. That means the page table is 2 to the 56. That's actually literally impossible. That's just, that can't be done. With a 64-bit computer, you have to actually take everything we're doing. Well, you have to really change the whole nature of how page tables work, because the page tables become impossibly large. With 32-bit computers, page tables weren't bad. We just said they were a megabyte. But with 64-bit computers, page tables are literally impossibly big. So there has to be a whole new, there had to be a new way to do page tables. And I don't even know if we'll talk about it, because it gets to be kind of complicated. And it's not really what programmers need to know. If you understand the basics of page tables, the way they were done with 32 bits. So if you stick with 32 bits and you stick with the 32-bit way page tables work, you really understand everything a programmer needs to know. Okay. If you really want to understand modern operating systems, then you have to understand how they do 64-bit how they do page tables with 64-bit address spaces. But it adds another quite a bit layer of complexity. Okay, so page tables are not trivial. Okay? They take some getting used to, and they can just keep getting more and more complicated as you go into them. We're going to do the basics of page table. We're going to, for example, we're going to stick to 32 bits, because you can really describe elegantly. Page tables worked great with 32-bit computers. They start, with 64-bit computers, they started really having trouble, and they had to come up with some clever ideas to make page tables work with 64-bit computers. Okay, and if you go to our textbook, he talks about that in this chapter. We're going to skip this chapter, advanced page tables. We'll end up skipping that chapter, because we want to talk about what's in these two chapters, 21 and 22. That's when we add the hard drive to the picture. So we're talking now about chapter 18. So we're talking today, and probably on Monday we'll also still talk about chapter 18. Then we'll look quickly at this chapter 19 on something called the translation look-aside buffer, which is a way to speed up the way page tables work. Chapter 20 is, what do you do when you get these monster-sized page tables? Okay, and if you want, you can read about it. It's kind of interesting. If you want to, they have one idea is something called a multi-level page table. Another idea is something called an inverted page table. There was actually several different ways to do these things. See, does he have Yeah, the other idea was inverted page tables. Okay, so there are several different techniques that people used to handle the problem of monster-sized page tables. Okay, but what we're really interested in, that programmers do need to know, is this stuff about swapping. How do you add the hard drive into the picture? That's real important. So we're doing chapter 18, then we'll briefly look at chapter 19, skip chapter 20, then we're going to do 21 and 22 real carefully. Okay. And your homework assignment's going to have to do a little bit like with this chapter 17. We'll go back but chapter 17 is very Linux based. So we're going to do one more programming assignment on virtual memory, and it's going to be kind of like a little bit like what's in chapter 17, but using the Windows library, not the Linux libraries. Okay. All right. Let me show you another picture that I think is a pretty good picture for understanding. Here's a picture that somebody drew for address translation. So this is a combination of this picture and this picture. So it's trying to combine the ideas of those two pictures, okay? So here's the address that's coming out of the CPU. Here's a virtual address. It's chopped up into two pieces. And he's saying there's n bits in this one, okay? He didn't even say how many bits are in the offset. This is the virtual address. You want to see how to build the physical address, okay? So this part of the virtual address becomes an index into the page table. But he actually adds an interesting thing here. The page table is in memory somewhere. The page table, actually, I said earlier that the page table would be inside the CPU, that this was in the CPU. Turns out you cannot have 4 megabyte page tables sitting inside of a CPU. So the page tables actually are themselves stored in computer memory. They're stored in the kernel's part of memory. So in physical memory somewhere, down at the bottom here, you'd have the operating system. So I didn't, in this picture here, I could really add that down here is the operating system is down here. He's got his own part of memory. Okay, so he's got his own part of memory. The page tables are down here. So over in this picture, he points out that the page table has to have an address in memory. So you have to take the index into the page table and add it to the address of the page table. So this register here holds the address at the top of the page table. So you add the offset into the page table to the address of the page table, and you get a page table entry. The page table entry has got the page frame number. That was this left half. He put his page frame numbers on the left half of his page table. I put the page frame numbers on the he put his on the right half of the page table. I put them in the left half of the page table. So you go here to the page frame entry, the page table entry, and you get this frame number, and it goes up here and becomes the left half of the physical address. Meanwhile, this half of the physical address just gets copied into the right half. Okay. Now, what he doesn't show in this picture is the idea that you are supposed to check this stuff. You're supposed to do an if statement. He kind of left that off of the picture. You're really supposed to like what happens, you have to check that you have to check the bit over here that says that this number here is valid. And if this number isn't valid, then you send the signal back to the CPU. So he doesn't quite show that in this picture here. Okay. Then this frame number here, the frame number picks this frame. See, the frame number picks this frame in physical memory, and this offsets you into the frame. Okay, he actually should have, this offset over here in this picture would have been a frame in virtual memory. This is a page frame in physical memory, and you can see the offset is this little blue box here would have been the same little blue box over here in virtual memory, and this offset was how far off you are from the top of the frame. Okay, so this picture is another way to summarize address translation. Notice that n bits go in here, m bits come out in over here. That's this is 20 bits go into the index of a page table, and 36 bits come out as a page table entry. So there's 20 bits of addresses over here, and there's 36 bits of data in here. Okay. In his picture, he shows it as, whoops, the page number's n bits wide. It's used as an index into the page table. And then there's m bits over here. This number here could be bigger or smaller than this number here. It's actually, we'll see as we talk more about this, it's not that unusual to translate from a large virtual address space to a smaller physical address space, or vice versa. You could have the physical address space be smaller or bigger than the virtual address space. Right now, we have the virtual address space being bigger than the physical address space. The virtual address space is 64 bits. The physical address space is 48 bits. So on a modern Pentium computer, the virtual address space is bigger than the physical address space. But a few years ago, when we were using 32-bit computers, there was a time when memory was cheap enough that even though you had a 32-bit computer, which only had 4 gigabytes of virtual address space, it was possible to put more than 4 gigabytes of physical memory in a computer. So there was a few years where servers had more physical memory than they had virtual address space. So you would have each virtual address space was 32 bits big, and so that would represent 4 gigabytes of memory. But you could have 8 gigabytes over here in the physical address space. Okay, so that was common on servers about 10 years ago, 10 or no more like maybe 15 years ago. The virtual address space was large. I'm sorry, the virtual address space was smaller than the physical address space. Right now, the virtual address space is bigger than the physical address space. So it can go either way. You know, this n and this m can, either one of them can be bigger than the other. Okay, the theory of page tables doesn't say whether, doesn't say that the virtual address space must be bigger. A lot of people think that's what it always is. A lot of people think that the virtual address space is always bigger than the physical address space, because that's the way a modern computer is. But it wasn't really unusual at all to have it the other way around, where the physical address space was way bigger than the virtual address space. That meant you could put whole processes, you could put, like, if you had a virtual address space was 4 gigabytes and the physical address space was 8 gigabytes, you could put 2 whole processes in physical memory. Each process could have, each process could have its whole virtual address space sitting inside of physical memory. Okay? So that was actually done for a while with servers. Okay, all right. So what we'll do is on Monday we'll keep on talking about. We're still going to be talking about this chapter on the paging introduction. So we haven't really finished what's in that chapter. We just introduced the idea. So we'll finish that, and we'll probably start with the next chapter, translation look-aside buffers. Okay, it's a way of speeding things up. Okay, so next week we'll finish the basics of page table and do a little bit of the of this thing here, and then the following week after that we'll start looking at more advanced features of page table and adding the hard drive into it. And it just takes time. When you're home studying, I think the best thing you could do is write down all these words. There's a lot of words in here. You can see them: virtual address, physical address, page table entries, frame numbers, page frames, offsets. Write down all those words and try to be able to write out your own definition for each one. That's a real good way to study this stuff, is to build up your own, try to do the, and there's more pictures. You might look at this one here. I gave you just handouts that were from other schools. I think people have drawn some clever pictures. So if you go through some of these PowerPoints I've put in this folder, you can see that people have kind of drawn some interesting pictures to help you think about how this stuff works. So look at these pictures and make sure, when after a while you look at that picture and it'll all make sense to you. You know, you could draw it yourself. That's another thing you do. When you can draw that picture yourself, that's really good. Draw the picture yourself, check it against one of these pictures. So there's a whole bunch of different ways you can think of virtual memory. There's no one right way to think about it. So look at some of these entries in here. I gave you a few examples. And then we'll also next week look at code. Here's some code that actually does virtual memory accesses. Okay, so we've run out of time. Okay. If you have questions, please send me email, especially with the homework assignment. If you have questions about the program assignment, send me emails. And if you want to talk to me, you know, let me know. We can always meet with Zoom and talk. Let's see, where am I? Oh, did I do that? Okay, so okay, all right. So okay, I'll end the meeting now. You know, if you have questions, please let me know. Okay, so I'm going to end the meeting. Goodbye.